Hi, everyone. Welcome to the fourth session of this course that will last for we'll have another four sessions during the coming 2 or 3 weeks. Today, we will talk about pressure and volume, basic calculation of pressure and volume. I'm not formal today, but you might notice, because I am at the beach now. I know that you see walls behind me, but I mean it, so you can concentrate on what I'm saying, not on the bikinis on the beach. Hope you will enjoy this 1 hour. And as I said, we will talk today about very basic calculation of pressure and volume. You can ask me any question during the session, and I will try to answer it or try to hide, but I never hide, by the way. And if I don't know, I will tell you I don't know. Simple as that. We need to know that some abbreviation we use in oil field industry, like WHP, which is the wellhead pressure. We measure it with a pressure gauge on the wellhead. And we need to know the maximum allowable wellhead pressure, the pressure test we do on site. We need to know what's WP, which is the working pressure. Working pressure, manufacturer design his equipment as per. TP stands for test pressure. Test pressure, this is what we mean when we do pressure test for our equipment for the pressure of certification. And it varies from a standard to another, but if we are using the API standard, American Petroleum Standard, which is the most famous standard in the world for the oil field industry, the relation between the working pressure and test pressure is minimum 1.5. So if we have a piece of equipment like this one, we need to test it. If its working pressure is 5,000 psi, then after a year or so, we need to recertify it. So we need to apply pressure test for the purpose of certification. So when we take this piece of equipment to test, we have to do this test bay, authorized test bay, certified test bay, where we raise the pressure up to, as per the API, 1.5, the working pressure. So if this is a BOP, blowout preventer, for example, so when we test this blowout preventer, if it is working pressure, its working pressure is 5,000. When we do the test for the purpose of certification, we will test it to 7,500 psi. 1.5 at least. If it was the test, if you remember the first session, we said that when we issue the certificate for this BOP, it will be 5,000. We will never mention the 7,500. And I said that the difference between 5,000 psi, which is the maximum allowable test pressure we do in the field for this particular BOP, and the test pressure we did in the test bay for the purpose of certification, which is 7,500 psi, this difference, it is not to be used in the operation. This is to save your life in case of emergency. API, American Petroleum Institute. This is the organization, they put standard for the design, test criteria, contingency plan that we follow, operation procedures. NACE stands for National Association of Corrosion Engineers. This is related mainly actually for the material we are using, especially the H2S. You need to know ISO, for example, which is International Organization for Standardization. ISO is related to actually, it's mainly for managerial and documentation procedures that we have to follow. This is a very interesting issue, which is the NACE MR-1-175, which is related specifically for H2S, because H2S is, it's nice to know that it's not a friend of you. It is something really you need to avoid. It can kill you in no time, as you know. So, and one of the nice questions that came in the exams, it's about a BOB rated for 5,000 psi, standard, not for H2S service. This is a standard BOB which works in standard conditions. Its working pressure 5,000 psi. The story says that you rig up on a well and you test. Oh, we have some questions. Just a minute. Hi, sir. Can you send us the course in our email format PDF? This will open a hell for me, but send me your email and I will do it harder. Another question from Fatima. I cannot see the presentation. I cannot help you on that. Actually, it's Dr. Ahmed Al-Garhi has to know what's the problem. Most probably it is in your laptop, yani, not in ours.
The presentation is clear.
Yes, fine. Okay. Okay. Back to this H2S, and the story say that you have a BOB rated for 5,000 psi, standard service. You rig up on a well. We did a pressure test. We did the job. We finished the job. We dig down. Then we mobilize to another well. We rig up on the other well to do the other job. And when the operator, by the moment he rig up the BOB on the Christmas tree of the second well, he said, oh my God, this BOB I'm using now, which I use it on the previous well, standard service, but the previous well was H2S. So he used his BOB, which is standard service, on a well, which is H2S, but luckily, the job went okay. He had no problem, and everything went okay. The pressure test went okay. The job went okay till he finished, and he is released from that well without any problem. The question now is, this BOB, which is standard service, that he used it in H2S well before, can he continue? Can he start the second job based on doing a pressure test initially? And if the pressure test went okay, that he can continue the job? Can any one of you answer this question? I am waiting, trying to see your questions. You keep sending mails. I will be able, if I don't know if Dr. Ahmed can record this mail or not. But regarding my question, finally I got an answer from James. He said he cannot continue to do the job. Do you agree with this answer, or you have some other answers that as long as we did the pressure test, we can continue? The answer is he cannot. He cannot continue. The problem now is not with the pressure test. The problem we have now that this VOB, the H2S already has been segregated through the material itself. it destroys the material of this BOB. So the best scenario, I believe, to do with this BOB is bring big plastic bags, put it inside, close, and put it aside, beside the wall. The BOB is not suitable for work now. The H2 is destroyed. This is very dangerous. Please don't play with it. In oil field, we work in this green color area. This is what is allowed in the oil field. We work with the working pressure and the test pressure we do, which is at least 1.2 maximum expected during this job. This is the area of pressure we are dealing with in the field. What is written in red here, which is the test pressure for certification. This is not allowed in the field. This is allowed not even in your yard, it is allowed in a certified test bay to protect yourself, your life, if anything happened during this high pressure value of test. If we exceed this pressure, then we are in destruction deformation. Don't try to reach that, of course. What's pressure? It's a very simple question that we can answer easily. I believe it is force by area. Pressure is force divided by area. Very simple. But let me go to the second question, maybe a little bit harder. What is the hydrostatic pressure? If we agree that pressure is defined as force by area, then I ask you, what's hydrostatic pressure? I'm waiting any answer till I check your questions. One question I got here, what's the test bay area? Since we are dealing with high pressure and you cannot let people expose in this particular area to this hazard pressure, so the test area is normally can be just an area underground, and where you have a room with a glass anti-bullet, and you have screens to see what's going in the test bay. So if during this test, when you test a device and it explodes, you as a human will not be affected. You are in a safe area. And this explosion will not go in a far area because this area is confined. Normally it is concrete, very solid concrete blocks, preventing this explosion to be in a separate, in a big area. And as I said, what you can see is from anti-bullet screen glasses that you can see what's going on in this room in a safe area. This is quickly what's test bay. Another question I have, how can H2S destroy the material? It's a toxic in my knowledge. Yes, it's a toxic, but if you try to deal with that, it is not just a toxic. The H2S will go through, will enter the metallurgy of the material itself and destroy it. This is an answer to my question. What is the definition of hydrostatic pressure? One of the answers I got, it is the pressure created at the surface. This answer kills me because the hydrostatic pressure at the surface is 0. So there is no hydrostatic at the surface. We'll go through that now. Another answer is it is pressure applied by the fluid column in the well. Oh, we are close to the good answer now. It is the pressure applied by the fluid column in the well. Not necessarily in the well, actually, but in the sea, in the glass of water, yani whatever. Yani. But yes, I need to modify your answer a little bit by saying that vertical column of flow. Vertical column of flow, not just a column of flow. So I will consider your answer is correct. And if you go to the hydrostatic, I'm just skipping this because this is for the really well intentioned course, which is not our case yet. I believe you guys know the porosity and permeability, but if we go through it quickly, what's porosity before we go to the hydrostatic pressure? If what you see in these slides, these circles, these balls, if these are the grains, the formation grains at the bottom, these are the pore spaces. These are the pore spaces between the grains. If there is no pore spaces, there is no movement of fluid through. This is the porosity. Permeability, it is measured ability of fluid to move through the rock. Like this example, we have these rocks and you open the tap, water can go through. These are the permeability. If you see it here, these are the permeability. There is a permeability of fluid to move through this type of rock. If we go back to the H2, the hydrostatic head pressure, what is the definition of the hydrostatic pressure? Hydrostatic pressure is two words actually, hydro and static. Hydro means fluid, static means stationary, static condition. And the formula we are using in calculating the hydrostatic head pressure, it is hydrostatic head pressure equal TVD, which is true vertical depth, times D, which is density, times constant, which is 0.052. If this is the well, when we drill a well, as you see, this well is deviated. So when we run pipes here, the length of pipe that we run, it is MD, measured depth. But when we deal with the pressure, we don't care about the MD. We care about this area, this distance, which is the true vertical depth. This is how we measure pressure, true vertical depth. And we are using this formula because we are dealing now in this course with API. So API, so the pressure is PSI, pound per square inch. The distances, we measure it with feet. The density, we measure it with ppg, pound per gallon. The volume with barrel, capacity barrel per foot. This is the API units. But if I'm using other standard like SI units, then the formula will be changed. It will be hydrostatic pressure equal rho GH. But this is not the case here as API units. This is example, find the hydrostatic pressure in PSI of fresh water at 500 feet TVD. So this is the DVD we have. What's the density of water? It's the standard. In fresh water, its density is 8.33 ppg pound per gallon. So you just multiply 500 by 8.33 by this constant, then you got hydrostatic. We have another terminology we use, which is the pressure gradient. What's the pressure gradient? It is the hydrostatic head pressure per 1 single feet. Hydrostatic head pressure per 1 single foot. This is the definition of what's pressure gradient. If this is the case, I can easily say that what is the hydrostatic head pressure in another term? I can say it is the TVD times the pressure gradient. Because the pressure gradient is the hydrostatic head per foot multiplied by the number of foots, then you got the hydrostatic head pressure. From these two formulas, HP, it goes back, down, HP. Let's go to the other side of the formula, TVD, it went all the way down, TVD. But here it was density times constant. By the time it goes down, it became PG, which means that what's PG? It is density times constant. These are the three formula we are using in calculating the hydrostatic pressure in a very simple way. And what you see at the bottom of this slide, to find bottom wall assembly of two fluid columns or more, simply add the hydrostatic head pressure of the fluid column of the same unit of measurements together. Means that if you have a well, you have 2,000 feet of water, then 3,000 feet of oil. To calculate the hydrostatic pressure at a certain point, you have to see what's above it. This portion of water above it, you have to calculate its hydrostatic head. Then the portion of the oil, you have to calculate the hydrostatic head. Then you add two together. Like here. This is the data we have in this example. We have the water density at the bottom, 8.33 ppg. We have the oil density, 8 ppg. Then we have the oil level, measured depths and TVD. We have the water level, measured depths and TVD. Now he needs to calculate the hydrostatic head pressure at 8,000 feet. This is the 8,000 feet. If I'm sitting here, I have to see what's above me. What's above me actually, it is 1,000 feet of water. Then I have to calculate the hydrostatic head pressure of 1,000 feet of water. Then I have oil. The oil level here, it is 7,000, but this is not the figure I'm using because the oil is filling only this part from 2,000 to 7,000. So the column of oil I have, it is only 5,000 feet. So I have to calculate the hydrostatic head of 5,000 feet of oil. Then I add this plus the hydrostatic head of the water. This will give me the hydrostatic head pressure. Then you might ask me, but Ahmed, I have to calculate what's above. I don't know what's above. I didn't give you any data about what's above. But if I tell you that this first 2,000 feet on this well, the first 2,000 feet is full of gas, and this is shut off, and you have 500 psi shut in pressure, then you have to, in this case, you have to add this 2,000 feet of gas, the hydrostatic head, plus the shut in pressure, which is 500 in this particular case. The other type of calculation, pressure calculation we need to calculate is what you see now. This is the data I'm giving you. I have a well depth. I'll give you the measured depths and the TVD. This is to examine you which depth you will use, the TVD or the measured depths. We agreed that when we deal with pressure, we deal with the TVD. When we deal with Volume, we will deal with MD. And you have the formation pressure gradient, and we have the gas pressure gradient. This is the gas well. What does he need? He needs to calculate the well bottom hole pressure. The bottom hole pressure. So now, if this is our well, but we have no perforation, so this is just a pipe now. If I need to calculate, if I fill this bottle of glass with water to calculate the bottom hole pressure here, this is actually the hydrostatic head of the water above it only. But now, in this case, it is not just a closed system. We perforate this pipe. And now we have fluid filling this pipe, and we have a newcomer. We have fluid and pressure coming from the formation entering my pipe. So if I give you now a pressure gauge, please concentrate on, because this is the question I need you to answer. If I give you a pressure gauge now, and I ask you to take this pressure gauge and go down to this well inside the 3.5-inch tubing, you go all the way to the bottom of the well. Now you have the pressure gauge in your hand. Please see what the pressure gauge in your hand read and give me a call. When you reach the bottom of this well, the pressure gauge in your hand will read the hydrostatic head, which is the fluid above it, or the formation pressure that comes from the formation into the well, or the sum of both, or the extract of both. May I repeat the question? Now I have a well. The well is full of fluid. I gave you a pressure gauge. You go down all the way in. So you are in front of the formation now. And I'm asking you, can you tell me what the pressure gauge in your hand will read? And the four answers you might select, one of them is, it will read the hydrostatic head pressure, or it will read the formation pressure, or it will read the sum of hydrostatic head and the formation, or you have to subtract both. I need an answer. Let me see if you have an answer to my question or not. Okay, I have some questions. Now, some of you guys, the sum of both. And some of you said the difference between the hydrostatic and the formation. Subtract both. You have to add both of them. The fluid pressure, the formation, the hydrostatic pressure plus the formation. It will take the absolute difference. Type. Let us make it more simple. Forget about my question. Let's go to the yard. And you grab a pipe, 4-inch pipe, 4-inch pipe. Please make a hole on the top, put a nipple, needle valve, and the gauge. And at the bottom of this pipe, please make 4 holes, get 4 nipples, 4 valves, and let us connect 4 compressors. One compressor will give you 100 psi. The second one will give you 200. The third one will give you 300. The fourth one will give you 400 psi. Now, start the 4 compressors. So the 4 compressors are working now. Open the 4 valves. So the 4 compressor will feed air to this pipe, which you have a pressure gauge on top. The pressure gauge on top will read how many psi. What you have is 4 compressors. First one will deliver 100 psi. Second one will deliver 200 psi. The third one will deliver 300 psi. The fourth one will deliver 400 psi. My question is, what the pressure gauge on this pipe or on this manifold will read? Let me see your nice answers. I got some of the answer. One of you guys said 400 psi. The other one, some other ones say 100 psi. 400 psi. This is Sam Magdi said 400 psi. So I have 100 and 400. Any others? I'll wait a few seconds more before we go through. $400 psi, 700 psi, 400 psi. I'm laughing. Sorry for being smiling, Yani, but one said 4,000 psi. This one is joking. 400 psi. The one who said 700 psi, what he did actually, he said 100 plus 200 plus 300 plus 400. No, even that, it's not 700. The answer is, these 4 compressors are working now. You open the 4 valves, so air will be fed into this manifold. The compressor that feed this manifold with 400 psi, none of the other compressor will work. Because the one with 400, it will feed this manifold with 400 psi. So this manifold is 400 psi. You have a compressor 300 psi. How it will go in? 300 cannot access the 400. The other 3 compressors will not work. The pressure gauge, when he was a kid, goes to the school, we learned him, Mr. Pressure Gauge, you read the highest. If you take this pressure gauge, if you turn it upside down and you take this backside out, look inside, there is no calculator. The pressure gauge doesn't know calculations. He has been learned when he was a kid. He will go to the highest pressure and he's, yes, sir, you are my godfather. He will go to the highest pressure. This pressure gauge on top of the manifold will read 400 psi. None of the other compressor will work. So the aim of this is, back to my question, the pressure gauge in your hand, and you are sitting now 10,000 feet, will read what? Will read the highest pressure. If this well is dead, the pressure gauge in your hand will read the hydrostatic head pressure. If the well is alive, the pressure gauge in your hand will read the formation pressure. The pressure gauge reads the heights. He cannot calculate anything. I hope you agree with me on this. So in this particular question, the pressure gauge in your hand, and you are downhole now, We read what? We read the highest. In this calculation, the highest is the formation pressure. If you calculate the formation pressure, you will see that it is higher than the hydrostatic pressure. Let us go for that. What's the bottom hole pressure? The bottom hole pressure in our case, as we agreed, this will be the formation pressure. Do I have the formation pressure? Of course I have it. I have the formation pressure gradient multiplied by TVD. This will give you 4,503 psi. But I have to make a single full stop here because I need to discuss little issue with you. What I said now, that the formation pressure equal the bottom hole pressure. You calculate the bottom hole pressure, which is the formation pressure. If both are the same, this well is dead. There is no flow. For any well to flow, you have to have what we call drawdown. What's the drawdown? It is the difference in pressure between the formation pressure and the BHA, the bottom hole pressure. If both are the same, there is no movement. We are sleeping. There must be a difference. What bring, when you perforate, what bring the oil in this reservoir that is 20 meters away? It is the differential pressure. If pressure is the same, we are sleeping, we are not moving. But since here, this is not a course of calculation, we take it the very simple way. But of course, there is a drawdown. There should be a drawdown. Second requirement in this question is find the maximum surface pressure. Now, if the bottom hole pressure of this well is 4,503, what do you expect the maximum surface pressure? If we just neglect engineering and let's use the common sense, this is our well. Now I am at the bottom. I have 4,000 psi. This 4,000 psi will move upward, all the way up. If there is nothing on top of that, so this 4,000 will go all the way to the top, 4,000 psi. Actually, this 4,000 psi, if it needs to move upward, there is something above it, preventing it from moving upward, which is the hydrostatic head above it. So the maximum surface pressure on top, it is actually the bottom hole pressure minus the hydrostatic pressure. This is how we calculate the maximum surface pressure. It is the bottom hole pressure minus the hydrostatic pressure. In our example, we already calculated bottom hole pressure. Do we have a hydrostatic head pressure? Of course I have. I have the data. I have the gas pressure gradient multiplied by TVD. This will give you the hydrostatic head pressure of the gas, which is in our example 632. Deduct this amount from the bottom hole pressure. This will give you the maximum expected surface pressure, which is in our case 3,871. The nice part of engineering that calculations or numbers tells you if you are on the right track or not. And if you calculate the maximum surface pressure and you find it greater than the bottom hole pressure, you are wrong. Because in any producing well, the highest pressure is the formation pressure, of course, unless this well is dead. The third question, working pressure for the wellhead. If I need to purchase wellhead equipment for this well, should I get it 2,000 or 3,000 or 5,000? definitely I have to get it more than 3,871. So I'll get it definitely 5,000. Maybe some of you will say, Ahmed, just a minute, let me check. So he grabbed his calculator, he multiplied 3,871 by 1.5. So the answer is 5,801. Ahmed, we should buy a Christmas tree 5,801. And when he tells me that, I said, fine, let us go get it. Are you going to find it? You will not find. There is no standards. The Christmas tree is either 3,000, 5,000, 10,000, 15,000. But if you need to have a tailor-made Christmas tree, which is rated for 5,801, yes, we can make it. But you have to wait 2-3 years. And the price will be greater than the one which is 15,000 because it's not standard. The fourth requirement in this question is find the minimum kill fluid density. If we need to kill this well, what density we should, what's the minimum density we should use? So D density is the unknown. What is the known? The pressure gradient of this well. The pressure gradient of this well is 0.57 psi per foot. Is there a relation that combine this D and PG, density and pressure gradient? Oh yeah, yes, we have. We have this formula that says that what's pressure gradient? It is density times constant. In this formula, we have one unknown, which is the density. This formula. So divide this constant, divide the pressure gradient by the constant will get you the density, which is 10.55. And if you remember when we talked last session about the hydrostatic head pressure, when we kill a well, we should we have overpressure between 200 and 300 psi. I tell you yes, but in this question he was smart enough. He told you the minimum. The word minimum means what makes balance. This is what makes the balance. This is what makes the hydrostatic head exactly 4,503 psi. In this case, the well is dead. If the wellhead, if the bottom wall pressure equal hydrostatic, the well is dead. Yes. Let me see if you have any comments here. Okay, we are on the same track. Let us move now from the pressure calculation. And please, I said please 3 times, remember. Bear in your mind that the simple calculations we did, it's not that real because in our calculation, we ignore many factors affecting our calculation, like thermal expansion, like friction loss. So just keep in mind that this is just a simple calculation, not deep in details. When we talk about the pumping, in API system, we are using API, so the volume is barrels, the capacity is barrel per foot, and this is the difference between the capacity and the volume. Volume is barrel, but the capacity is barrel per foot. So here is the data we have in this question. We have a casing capacity, we have a tubing displacement capacity, we have tubing capacity. Then we have a pump displacement, which is barrel per stroke. This is the piston pump. The piston pump we measure how many barrel or liters, gallon, the piston of this pump is pushing every stroke. Stroke means from A to Z. The piston moves from A to Z. It displaces 10 liters, 10 gallons, 5 liters, 5 barrels. This is what we mean by pump displacement. And at the end, we give you the tubing shoe. We give you measure depths and the TVD. Before we start, I have a very simple question for you to answer first. Please tell me what's the difference between tubing volume and tubing displacement volume. Again, I need the difference between tubing volume and the tubing displacement volume. Let me see your answers. Some people ask, can we get this presentation? I have no problem at all, but the one who can deal with you guys and send you is Dr. Ahmed Al-Garhi, of course. Shihab said the tubing volume is the total volume that fill the tubing. Fine. Then what is the tubing displacement volume? Thanks, James. It's a very interesting question. Tubing displacement volume is the differential volume created as the result of tubing displacement. I think this question, who can understand it, is William Shakespeare. I cannot understand what you said, Faman, Allah. But, James said tubing displacement volume is volume per unit length. I'm afraid I cannot accept this answer. Tubing volume is the volume of the tubing. The tubing displacement volume is the volume of fluid displaced when the tube is plugged in. I'm afraid it is not an answer. Tubing volume is the total volume, and tubing displacement volume is the one which the stroke time. I gave you enough time to think and feed me back. Let me go to my glass of water. Let us assume that this is our well. We drill this well, and then we run a casing. Then we fill this well with water. And let us assume that we fill this well with 500 barrels. 500 barrels. If I ask you now, what's the total volume of this well? It's 500, which is plus or minus the casing volume. Now, after we run the casing, this well is full of water. We are running now the production tubing. Let me run the production tubing now. While running the production tubing now, what's going on? What's going on? I'm afraid that my shirt, my trouser, my short, actually, I'm not wearing a trouser, I'm wearing a short. I'm on the beach now. My short is getting wet, right? This well is full of water. So the moment this production tubing enters, water comes out. This is the water displaced. By what? By the metal thickness of this production tubing. So by the time I finish running the production tubing, 50 barrel is out. What is this 50 barrel? This 50 barrel is the tubing displacement volume. This is the volume displaced by the metal thickness of the production tubing I'm running. So the tubing volume, yes, it is how many barrels I can fill the tubing with. But the displacement volume, it is the amount of fluid displaced by the metal thickness. So back to my well, it is full of 500 barrels of water. I run the production tubing all the way in, 50 barrels is out. What is this 50 barrel? We agreed that this is the fluid, the displacement volume. This is the tubing displacement volume. My second question, what is the total volume of this well now? What is the total volume after running the completion? What is the total volume of our well now? Oh, I hope I receive any answer. I'm very interesting to receive answers. One said 500. One of you guys said 500. Any other answers? Any other numbers? My well was full of 500 barrel. I'm running the production tubing. When I run the production tubing, 50 barrel is out. My question, what is the total volume of this well in front of me now, in front of you now? I got some other answer. I got 550. I got 450. I got 500. The one who said 550, yani, this is full of 500. Can you fill it with 1 liter more than what it can withstand? I mean, it is full of 500. How you get it 550? This is 500. You run the production tubing. 50 barrel is out. What is the total volume of this well now? 450, of course. It was 500. 50 barrels is out due to the fluid displacement volume. What's the remaining? It is 500 minus the 50 that went out. So it is 450. The total volume of this well is 450. People who said 500, you will never see 500 again as long as the production tubing inside this well. This 500, it is the casing volume. But once you run the completion, 50 is out. You cannot regain this 50 out in the well. There is no way. This will be against the engineering. The total volume of this well after you run the completion definitely is 450. To calculate the total volume of the well, there are 3 ways to go. Let us go to the 3 ways. First method is what we just discussed. It is the casing volume, which was 500, minus a tubing displacement volume, minus L50 that went out. 500 minus 50. This is the total volume of the well. Or I can say after I run the completion, if I need to calculate total volume of the well, it is the sum of 2 things. It is the annular volume, which is the distance, the volume, the annular volume between the tubing and casing, plus the tubing volume itself. Both methods are okay. This third method, this is a special case. If you are running the tubing closed in. Let us go for this example. The data we have, please memorize this. We agreed that the data we have is the casing volume, 500 barrel, and we agreed that the displacement volume, tubing displacement volume is 50 barrel. I will give you one more data. which is the tubing volume itself. The tubing volume itself is 150. Three data you have now. Casing volume 500 barrel, tubing displacement volume 50 barrel, and the tubing volume 150 barrel. Let's go back to our well. It is full of water now, 500 barrel, and I'm running now the production tubing. But I'm running the production tubing closed in like plug. I have a plug at the bottom. Let me run it now. After I finish running, my question now is, how many barrels of water is out? The well is full of 500 barrels. I'm running the tubing closed end. I have a plug at the end. After I run, based on the data I'm giving you, that tubing displacement volume is 50 barrel, tubing volume is 150 barrel. After I run the production tubing plugged, how many barrels is out? Let me see your answers. Shoaib said 300 remaining total well volume because 500 minus 50 minus 50, 200 is out. 200 is out. I'm asking, what's the total volume? I'm asking how many barrels is out. So he said 200. I have more than answer was 200. 200. Okay. Type. It is my turn to answer the question. I have the well full of 500 barrels. I'm running the tubing closed in. If this tubing is not closed in, if I run it, what will come out is just the displacement of the metal thickness of this tube, which is 50 barrels. But now I am running it plugged. So while running in the hole, I'm not filling the tubing. So what comes out is the sum of two things. It is the tubing volume plus the tubing displacement volume, which is 150 plus 50. What comes out is 200. What comes out is 200 barrels. 200 barrels is out. Let me ask you the last question today. Now, this is full of 500 barrels. And I'm running the production tubing closed in. After I finish running, we agreed that 200 is out. 200 barrels is out. My last question today is, what's the total volume of this well now? And please, before you answer, count from 1 to 20, because this is a tricky question. Think twice before you answer. I am eager to see your answers. I didn't have any answer yet. I have 450, one answer, 450, I believe. $450. I'm really happy to receive such an answer. 450. I was looking for more than 2 to answer actually, but I have 4 answers now. They all went for 450, which is actually correct. 450. Why 450? And why I said this question is tricky, because many people said, very simple question, Ahmed. This is full 500. This is closed. You run it, 200 is out. The total volume of the well, the remaining is 300. So it is 300. I said wrong. 300 is the remaining, yes. But the 300 barrels you mentioned does not represent the total volume of the well. The 300 barrels you mentioned represent the annular volume only. Still, I can take 150 from out, fill the tubing with. It is the same pipe, the same well. 450 is still the same. So, in case of closed end, the total volume of the well, it is the casing volume, in our case 500 barrel, minus tubing displacement volume closed end, which is 200. This 500 minus 200, this represents the annual volume only. You have to add a tubing volume. You have to add a tubing volume. This is how to calculate the total volume of the well. This is the only 3 ways to go to calculate the tubing volume. And if you go here, if we go here with this data you have, and if I ask you if you need to calculate the tubing volume of the well, total volume of the well, which way you will go? It will be the tubing volume minus annual volume, or the casing volume minus tubing displacement volume, or the third case, which is the closed end. If you go through here, there is no closed end here. So the third way is not correct. And if you select the tubing volume, the total volume is the tubing volume plus the annual volume, you don't have the annual volume here. How you calculate it? But based on the data you have here, it is the casing volume, because you have it, minus tubing displacement volume, which you have it. So the first question here is asking, how many strokes to displace a tubing string? How many strokes you should do with this pump to get out of the tubing volume? Do I have the tubing volume? Of course I have it. You have the tubing capacity. You multiply it by the measured depths. Remember, when we deal with volume, we deal with measured depths. So we multiply it by the measured depths. So we have the tubing volume is 107 barrel. To get rid of it, how many strokes we should do with our pump? Divide this by pump stroke to get how many strokes. And the second requirement is just repeat, how is to displace the entire volume. The entire volume means a total volume. Total volume. The total volume of the well, in this case, it is, as we agreed, it is the casing volume minus tubing displacement volume. Casing volume minus tubing displacement volume, divide that by pump displacement. One step. This is how to get total volume. 1 hour passed quickly as usual. We exceed 1 hour now already by 5 minutes. I almost done with the calculations. Yes, I have a little bit to go through, but our time is limited with 1 hour. So I will see you next week, Sunday, 3 o'clock, Cairo local time. And this Sunday will be our 5th session, where we're going to start about completion. We'll have 2 sessions to discuss about the completion. Completion, to discuss it, we need 3 months, but this is a very simple. We'll talk about the accessories that we use, that we run with the completion, why we run these accessories, and how it works. I will see you Sunday, inshallah. Dr. Ahmed, I am done.
Engineer Ahmed, thank you very much. For sure, we will see you again Sunday at 3 p.m. Egypt time. Enjoy the beach.
Thank you.
And enjoy your rest of the day.
Thank you, sir, and thank you for the comments I received from you guys. Thank you much, inshallah.
Goodbye.